Welcome back. So we're going to continue with integration today, talking about definite integration, integration of trig functions, and the area between two curves. So I'm going to start out looking at our trig functions. Here on the left, I've got all of our derivative rules for trig functions. Again, because integration is the opposite of differentiation. If I derive sine to get cosine, then when I integrate cosine, I should be able to work backwards and get to sine. Integration's answering the question, what did I derive in order to get this function? So if I integrate the negative sine of x, I should get to positive cosine x, because when I derive cosine, I get negative sine. Okay, so this is really just working backwards. There we go. So if I integrate secant squared, I should get tangent. That's because when I derive tangent, I get secant squared. If I integrate negative cosecant squared, I'll get cotangent. Integrate secant tangent, I'll get secant. And integrate negative cosecant cotangent, I'll get cosecant. Again, just working backwards. All of these plus c's are because we have no way of knowing if there was a constant here. If I derive the sine of x plus 4, I would still get cosine. If I derived sine of x plus 47, I would still get cosine. So because there's no way of knowing whether there was a constant, we'll need to have a plus c on everything that we integrate as long as there's no bounds. Any questions on this one?
No.
Okay. So then we'll start looking at area. If I wanted to integrate from 0 to 5 of 1/4 x squared, then what I'm really doing is I'm getting the area between x equals 0 and x equals 5 underneath the curve of 1/4 x squared. So to do that, I'm going to do the same thing that you guys did for the homework. So I'm going to divide by dx, add 1 to the power, divide by the new power. So when I add 1 to the power, I'll get x cubed, divide by the new power. That'll be x cubed over 3 times the 1/4 is x cubed over 12. Again, plus c, because we have no way of knowing if there was a constant there. So for the homework, we would have ended here. But if I want to find out how much area there is between point A and point B, then I can plug in my upper bound and subtract my lower bound. So my upper bound is this 5. So I'm going to plug 5 into our equation, and then subtract what happens when I plug 0 into the equation. That will tell me how much our area has changed between x equals 0 and x equals 5. Okay, so when I plug in 5, this is 5 cubed is 125 over 12 plus c. Minus 0 cubed is 0 plus c. That c minus c will cancel. And of course 0 cubed is 0, so I'm left with 125 over 12. Any questions on what I did here? Okay.
So the answer is the area beneath the curve?
Yes, the sensor represents the area beneath the curve. What we're really doing is I'm taking an infinitely small box that looks like this, that has a base and a height. That base would be an infinitely small change in x, and my height would be whatever my height is right now. So if these are infinitely small and I keep adding them together, then what I'm really doing is I'm adding a bunch of infinitely small lines together. And if we keep adding all of those infinitely small lines together, we'll get the exact area underneath the curve. Units wise though, because this is a base times a height, I'm multiplying my units together. So if this had been, for instance, velocity for my y-axis, which would be measured in meters per second, and then time for my x-axis measured in seconds. Then when you integrate to get the area underneath the curve, I'm multiplying my y-axis times my x-axis, which would be meters per second times seconds, or meters. Okay, any other questions?
No.
Okay. Key here for definite integration, as long as you have bounds, that's a start point and an end point for the area that you want, you're always going to plug in your upper bound and then subtract your lower bound. Also, this plus c that we have for integration will always cancel. You'll always end up with a c minus c, so you don't have to write that plus c if you have bounds, because it will always cancel. If I was going from two different points, so not from 0, so let's say I want the area between x equals 2 and x equals 5, then what I could do is take all of the area here from 0 to 5, and then subtract all of this area from 0 to 2, and I would be left with the area from 2 to 5. So what that looks like is, again, an upper bound. So after we integrate, I'm going to get rid of the dx, add 1 to the power, divide by the new power, and I end up with x cubed over 12 plus c again. But after we integrate, I'm going to plug in my upper bound, so I'm plugging in 5, and then I'm subtracting what happens when I plug in my lower bound, plug in 2, which means I'm getting the total area from 0 to 5. That's what happens when I plug in 5. And then subtracting my area from 0 to 2, what happens when I plug in 2. We'll cancel this area from 0 to 2 out of the total area from 0 to 5, and leave me with just this area in green, which is the area from 2 to 5. Okay, when I do, this is 125 over 12 plus c minus 8 over 12 plus c. My plus c's will cancel. 125 minus 8 is 117 over 12. Gives us our area between x equals 2 and x equals 5, underneath the curve of 1/4 x squared. Any questions on what we did here?
No.
Okay. So going one step further with this, if I had two functions instead of just one, so a top function and a bottom function, I'm going to call my top function f of x, my bottom function g of x. So f of x here in red, and g of x here in blue. Then what I could do is take the area underneath my top function and subtract the area underneath my bottom function to get the area between them. Using this technique, we can get the area of pretty much any shape in 2 dimensions. So if you want to get the area between two curves, you can get the area underneath the top curve and then subtract the area underneath the bottom curve to get the area between them. Or I could say the integral of f of x, my top function, from a to b, minus the integral of g of x from a to b, which, because these bounds are the same, I'm moving from the same start point to the same end point. Same start point and end point, same start point and end point. And integration is really just repeated addition. So I'm adding these boxes of infinitely small base times height together. So that means as long as my start point and end point are the same, if I subtract my top function from the bottom function for every possible line that I could draw, then I'll end up with just the lines between them. This in different colors maybe. So here's the area underneath the red, and then for the same point, the area underneath the blue. If I subtract the area underneath the blue from the area underneath the red, I'll be left with just this area between the two curves. And if I keep doing that for every x value between a and b, then I'll end up with just the area between them. Any questions on what we did?
No.
Okay. You guys are really fast. I'm gonna
So we just subtract one function from another, basically, like the integral of one function from integral of another one.
Yep, and then because their start and end points are the same, if their start and end points are the same, then we can just combine these into one integral. So this will become the integral from your start point to end point of your top function minus bottom function.
Okay.
Wait,
Okay, Abby, did you have
so
a question?
what does it wrote here? Like, it says area between two curves, and then the three buttons just block the content.
Okay, you're saying you can't see everything, maybe?
I can't see like what this like. It says like A and then line B my fx minus g. Oh yeah, like I can see it now. It's okay. It's okay.
Okay. There.
So you just is it like B's? Wait, what?
You're asking what is A and what is B, maybe? A is your starting x value, B is your ending x value.
Mm.
F of x is your topmost function, so that's our function here in red. And g of x is our bottommost function, so that's our function here in blue.
Yes.
Okay, let me do an example, and we'll see if this makes more sense. And then if you can think of your question, we'll come back to it, okay?
Okay.
Okay, so I've got two functions here. I know this one's a little bit blurry, so I've rewritten it over here, but I've got my topmost function here, which is negative x squared plus 8x minus 10, or this function right here on top. I know that that's the function they're referring to because this is a parabola opening down. So that negative x squared is my clue that the function that's on top is the one that is, the one that is this equation. My parabola opening up is my x squared over 2 leading function. So that will be my g of x or my bottom function. So this is top and bottom. Okay, so my area between the two curves should be the integral from my start point to end point of my top function minus my bottom function. Now for this one, I was not given a start point and end point, so my first step, step 1, is to find the intercepts. So to find the intercepts, I'm going to set the y values equal to each other. So I'm going to set f of x equal to g of x. So that's f of x here, and g of x we'll plug in here. Okay, so I've got a negative x squared, and I'm actually going to get rid of these fractions first, I think. So let's multiply everything through by 2. If I do, that'll get rid of this fraction. This will be multiplied by 2. That'll get rid of this fraction, and then everything else is multiplied by 2. Then I'm going to combine my like terms. I'm going to move everything over to the right side, since that'll make my x squareds positive. So this is negative 2x squared. If I want to get rid of it, I'll add 2x squared to both sides. X squared plus 2x squared is 3x squared. Okay, to get rid of the positive 16x, I would have to subtract 16x from both sides. Negative 2 minus 16 is negative 18. To get rid of the negative 20, I would have to add 20 to both sides. Negative 5 plus 20 is negative 15. Okay, from that step, if you wanted, you could either factor from here, or you could divide everything by 3. If you divide everything by 3, this will become x squared minus 6x plus 5. And then we can factor from there to get x minus 5 and x minus 1. So our x values are either positive 1 or 5 to make this equal 0. Okay, so that gives us our bounds. I want to integrate from x equals 1 to x equals 5. if we're going to integrate from x equals 1 to 5. So we can integrate our top function minus our bottom function from 1 to 5. And combine our terms. So here's our x squared minus our x squared term. This is negative 2 over 2x squared minus 1 over 2x squared is negative 3 over 2x squared. Then I've got 8x minus a negative x is positive 9x. And negative 10, so that's negative 20 over 2, minus negative 5 over 2 is negative 20 over 2 plus 5 over 2 is negative 15 over 2. Okay, then I'm going to plug in my bounds, so I'm going from 1 to 5, and then simplify to get my answer. Any questions on what we did here?
No.
Okay, let me throw up a couple more examples, and then we'll stop there. Oops. Okay, so I did already work these out in the last session, so I'm just going to walk through the steps, I guess. And then I might generate one more random one, and we'll do that together. So if I wanted to find the area that is underneath the curve here, you'll notice how the area is actually above the curve because I'm below 0. So that's kind of my clue that my answer will be negative. So to start out, I'm going to take our integral, and we're going to integrate using the rules that we had from our last class. So that'll look like this. Add 1 to the power, divide by the new power, so this will become x to the 4th over 4. Add 1 to the new power, divide by the new power, so this will become negative 3x squared over 2. And do the same thing here. I did not have a power here, so that was x to the 0 originally. Add 1 to the power will become x to the first power over 1. Any questions on this first step?
Mr. Brandon?
Yes.
No.
Why is there is it why there's no plus c here because negative 5 is already c?
There's no plus c here because we have bounds. So when we had a plus c, and we were integrating with bounds, so like in this slide,
Yes.
you'll notice that at the end, after we plug in our upper bound and then subtract our lower bound, we always end up with c minus c, because there's a plus c in both of those, right?
Yes.
So as long as you have bounds in your integral, you don't need to write your plus c because it will always cancel.
So c will only exist if there are no bounds.
Yes.
Okay. Thank you.
No problem. So then, okay, we're good on this step. So the next step is to plug in upper bound and subtract lower bound. So that'll look like this. I'm going to plug in my upper bound into every one of these x values, and then subtract my lower bound plugged into every one of these x values, which would give me this. So I've got 2 squared is 4 times another 2 squared, so my 4 and 4 will cancel, leaving me with 2 squared, which is 4. One of these 2's will cancel with this 2, which leaves me with a negative 6 here, and then negative 5 times 2 is negative 10. Okay, then I'm going to distribute my negative. Negative 1 to the 4th power is positive 1, and then that negative will distribute, so this will become negative 1 over 4. This negative 1 squared will become positive. I've got a negative on the outside, so that'll be negative 3 over 2, and then I've got the negative that I need to distribute, which will become positive 3 over 2. And then the last term, I've got a negative 5 times the negative 1 is positive 5, and the negative that I distribute makes this a negative 5. Okay, then we can add all of these together. So I've got 4 minus 5 is negative 1, minus 6 is negative 7, minus 10 is negative 17. Negative 1 over 4 plus 6 over 4 is 5 over 4. Okay, 17 is 68 fourths. So this is negative 68 fourths plus 5 fourths is negative 63 fourths. Any questions on what we did here?
No.
Okay, I'm just
No.
going to double check here graphically. So we got an answer of negative 63 fourths. Negative 63 fourths is negative 15 and 3 fourths. So we should be able to see that on our graph, hopefully. So I'm just going to color some of these squares in, maybe. So here I've got... Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 total squares. Okay, 10, 11 are full squares. Okay, I'm going to say this square and this square is roughly 12. This square and this square is roughly 13. This square and this square is a little bit more than 14. So we call that one plus this one 15 and a little bit. Which is exactly what we were looking for. It's 15 and 3 fourths. Okay, again, that negative sign is just showing direction. It's negative because our function was underneath 0. So this is actually above the curve rather than below the curve. Okay, I'm going to do 2 more. So for this one, I've got our area between secant tangent and negative 2 cosine from negative pi 6 to pi 6. So if I subtract upper bound minus lower bound, the one we're more familiar with, this cosine, is going to keep bouncing between 2 and negative 2, right? Because we have an amplitude of 2. So that means this cosine function is really this function here. That keeps bouncing between 2 and negative 2. So the function we're a little bit less familiar with maybe is this secant tangent, which is this composite function here. So our top function is this secant tangent. So I'm going to subtract our lower function. If I'm subtracting a negative, I'm really adding a positive. Okay, then I'm going to work backwards. What function would I have to derive in order to get an answer of secant times tangent? Well, if I derive secant x, then I would get secant tangent. And then what function would I have to derive in order to get 2 cosine x? If I derive positive 2 sine x, then I would get 2 cosine x. Okay, so that's working backwards. Any questions on how we worked backwards with these trig functions? Okay, so I'm going to plug in upper bound minus lower bound just like we were doing. From our unit circle, at pi over 6, so I have a long side and a short side here. My long side is always root 3 over 2, and my short side is always 1/2. Okay, so I have secant plus tangent, secant at pi 6. Secant is 1 over cosine. My cosine at pi 6 is my x value, which would be here. So if my x value is root 3 over 2, then 1 over root 3 over 2 should be my secant, which is 2 over root 3. Okay, my sine at pi 6 is my y value. My y value right now is 1/2, so I can substitute that in. Okay, any questions on what we did with the unit circle? Okay, then I'm going to keep going for my next unit circle value. So we have negative pi 6, and that's the same thing as 11 pi 6, which would be here. I still have a long side of root 3 over 2, but now I have a short side of negative 1/2. So my secant is still going to be 2 over root 3. So my x value hasn't changed at all, but my sign is now negative, so this is negative 1/2 instead. Okay, and now we can add across. So I've got 2 over root 3 minus 2 over root 3 will cancel. And then 2 times 1/2 is 1, minus negative 2 times 1/2 is 1 plus 1, or 2, for my total area. Any questions on this one? Okay, let's try one more. So I'm going to regenerate these and make it random. And get the area between two curves. Sure. Okay, so we are finding the area between these two functions. Which function is on top right now? Cosecant cotangent or cosecant squared?
Cosecant squared.
Okay, cosecant squared is on top. So this is, if I wanted to integrate from our start point to our end point of top minus bottom, would look like this. The integral from my start point at pi fourths to our end point of 3 pi fourths. Of cosecant squared x minus cosecant x cotangent x.
Mr. Brennan, how did you type pi on the computer? Just pi.
Hit insert objects equation, and then when you're in equation, if you type a backslash and then write pi, it will convert that to pi.
Okay.
Alternatively, when you're in the equation window, you've got all of these options for things that you can paste. If you hover over it, it will tell you what the code is. This one's backslash pi
Okay.
if you want to type it out. If I wanted mu, this would be backslash mu. So you can do all your Greek letters that way, and then a couple different functions. Okay, so here it is again. Insert equation. Okay, so I'm going to integrate this. If I integrate cosecant squared, what function could I derive in order to get cosecant squared?
Tangent.
If I derive tangent, I get secant squared.
Oh, secant squared. Sorry.
Negative cotangent?
Negative cotangent, perfect.
Oh.
So if you derive positive cotangent, you get negative cosecant squared. So if I want to get positive cosecant squared, I should derive a negative cotangent. So my answer would be negative cosecant squared or positive cosecant squared. Okay, and then if I want to get a negative cosecant cotangent, what function would I derive?
Cosecant?
Cosecant, perfect. Okay, and then I need to plug in upper bound minus lower bound, so to subscript that, I'm just going to write a straight line here, and then write my upper bound and lower bound on top of each other. So this is from pi fourths to 3 pi fourths. Okay, and then we'll plug in upper bound minus lower bound to get our answers. This will become negative cotangent of 3 pi fourths plus cosecant of 3 pi fourths minus our lower bounds of negative cotangent pi fourths plus cosecant of pi fourths.
But why are there 2 3 pi 4?
Because we've got two different functions that I'm plugging in for my upper bound.
Oh.
That helps.
No.
Okay, so this is all upper bound for this part here in red. And this is all minus my lower bound for this part here in blue. So I've got 2 3 pi fourths because I'm plugging into my upper bound part, which has two different trig functions. Okay, so then on our unit circle, oops, not drawing, there we go. On our unit circle, we have 3 pi fourths, which would be out here. At an odd number times 5 fourths, we have equal lengths for x and y. So at equal lengths, this would be root 2 over 2 for our magnitude. So this would be root 2 over 2 positive for my y value and negative for my x value at 3 pi fourths. And then at pi fourths, for our function in blue, that's also an odd number times 5 fourths, so my x and y lengths are equal. So this would be root 2 over 2 positive for my x value and root 2 over 2 positive for my y value as well. Okay, cotangent is x over y. So this is negative root 2 over 2 divided by root 2 over 2. That's the same number divided by the same number. Will give me negative 1. Plus the cosecant is 1 over y. So that'll flip my y value. This will become 2 over root 2. Okay, so that's all upper bound. And then I'm going to subtract my lower bound, which is negative cotangent at pi fourths, which again is x over y. So that's root 2 over 2 divided by root 2 over 2, which is 1. Plus the cosecant is my 1 over my y value. My y